Well, hello, this is Professor Urban, and the purpose of this clip is to demonstrate how a program works. Let's take a look at the program now. There it is, and I can put myself in the corner, and the idea here is that you've already loaded this program, and I'm going to demonstrate its operation. This is associated with the paper that's published now. So the first thing that you need to do, there's some simple instructions on the left. The first thing you do is load a set of trained networks. So I click on that button, and up should come a window, and it's over here, so I'll drag it over. And these are the selections from which you can choose. This is for the program, so it starts with the letters pub, and then the film is the first couple of letters underlined, and then the substrate is next. The number of training data set, and whether it was an 06 or an 05 program. The 06 works with 4 measurements, and the 05 works with 5 measurements, kind of counterintuitively. So, and you can see that there are several here, and there will be more when you get it. So let's just pick one, chromium on silicon. We'll take it trained to 10 to the 6th. Using the 06 version. Oh, that's BK7. And let's take this one here. I guess there's only 2. We'll take this one. And it loads it up, and it tells you what you loaded up. There will be more in due course. So the next step, step 2, is that we can take a look at the spectra. And we can change the 4 thicknesses at which the measurements are computed for the test. So when we press the button Pred Spectra, you're going to see the results that are obtained from a network, and it takes this long only, and they pop up on the other screen. This is the first, the last of them, which is the optical properties of the substrate. Next, and I'll shift that over here to the right, a little bit behind me, but that's okay. Next, the optical properties of the real part of the optical properties, or N of the substrate. So all of that has been determined from the measurements and the neural networks. Next, we can take a look at the thing we're more interested in, which is the optical properties of the film. This is the extinction coefficient of the film. And this is the real part, or N, of the film. Now, in order to see, gee, did we get it right, we should take these predicted values. Now, the predicted values are the red circles, and the target is the black. So you can see that it doesn't hit it precisely for every wavelength. And this is for 33, I think, or this is for 13 wavelengths, or 17, sorry. So let's see what happens if we go ahead and take the values of N and K of the film and the substrate and the 4 thicknesses, which we'll see in a moment, and feed them back through the Maxwell equations and see if they hit the expected value. The expected value is the dark, are the lines, the dotted lines, and a solid line for the 4 different thicknesses. And you can see it does a pretty good job. We could zoom in, and you could take a closer look. So if you want to zoom, you want to click on the little plus, make a box around what you want to see bigger, and then you can start to see how well it's hitting those, and it's hitting that particular set very well. If I double click, it'll revert. That is the value of delta. Interestingly enough, delta is not very different for the 4 thicknesses that are reported. And here we have psi, and they are a little bit farther apart, but bunched up here in the short wavelength range. And again, you can see a pretty good job. And we'll look at statistics after a minute. Finally, I'll show you the thicknesses. And these are the thickness predictions, and they were used in the calculation for those last 2 figures. And you can see that at the longer wavelengths, we seem to be having a lot better result than in the short. And I can go ahead and zoom in on this to get a closer look at it. If I pick like the longest wavelength, we can see that the thicknesses are extremely accurate. We'll see that again in a minute. And if we go to the longer wavelengths I meant, and then at the shorter wavelengths, it's not hitting it so well. What's the reason for that? Well, underlying all of this solution method is, surprise, surprise, it's the underlying physics. So what have we got? The value of N, let me bring it up, it's right there, of chromium is, reasonable metal-like substance. And now we're going to bring up the optical properties of the, well, that's the substrate. That's not what I wanted. And I think it's hiding a little bit. I'll have to move this and get to it. That's the substrate, and this one here, which is hiding a little. Let's get it out. Here we go. This is K of the film. Now, you notice that, first of all, the wavelength is shorter, so the light is going more wavelengths through the film, and the extinction coefficient is quite high. So the penetration depth is not as good at the short wavelengths, and that would explain what we have. Now I want to go back to, I'm sitting right over top of what I want to show you. And I should take my picture out. And if you click on this on your bottom, you'll see all the figures. You can pick each one you want. I'm going to pick the one of the program itself, and I'm going to close all those figures by clicking Close Figs, as you just saw me do. Now let's go to the statistics before I go to the targets. I'll hit Statistics, and it pops up on the other screen, and I'll bring them over one at a time in the reverse order. So again, to check and see, did we get our numbers back that we wanted? I put those, I'll slip over those, and I'll go right away to the one I want to show you, which is the root mean square error of the 8 numbers that we have predicted. Fair enough. So I'll put myself back in for a second. What is this figure here? The upper left figure is a wavelength across the x-axis, and the mean square error, root mean square error, is a bunch of dots. Now each dot is the result of 500 tests with 500 different input sets, and therefore 500 different predictions, each prediction consisting of the 8 numbers. If we take a look just of the value of n, which is predicted, for that particular dot right there, how is it produced? The 800 tests at that wavelength, and then we get 500 tests at that wavelength, and the 500 root mean square errors, and this is the mean of them. You can see that the value of n axis is 0.05, so this is about 0.01. And the n of the substrate was in the order of 2 or 3. So 0.01 or 2 It's pretty accurate, and that number can always be improved upon by training differently and making different choices in making your networks. So here we have a pretty good low level of mean square error. For n, this is for k of the film, and it can see it also is quite low on the standards. The thickness root mean square errors are very good. This is 1 nanometer, so this is a fraction of a nanometer, or less than an atomic layer. And then we come over here to the thickness measurements 3 and 4, same deal. And then I scooted it over so I can stay. And you see the accuracy with which it calculated the virtual substrate, N2 and K2. And if I want to get rid of all that, I have to just do close figs. Now we can also look at all 500 tests a different way. And that's by doing the target plots. If I click on that, it brings them up on the other screen. I'll bring them over. And you can start to see, we'll come back to this. But these are the ones I want to show you first, and that is the values of the prediction of, in this case, D3, D4, and N and K of the virtual substrate at 253 nanometer wavelength. So this is the detailed information about the predictions found at 253 for 500 random test sets, data sets, all 8 numbers found simultaneously, and then we feed it a test target in this range and see how close the prediction comes to that target. If this prediction, this one happens to be for N of the substrate, you can see that if it were perfect, then it would fall on this black line, which indicates a exact match between the target and the prediction. So there are 500 dots here, each one of them for the 500, each for one of the 500 tests. You can see for N and K, it's doing a nice job. For D, it's not as tight on the line. Interestingly enough, the mean square error is very low, which we already saw. But this is at the short wavelength. In a minute, I'll go to the long wavelength, and you'll see these bunch up. And here they are for 253 for N and K of the film, and D1 and D2 of the measurements, D1 and D2, similar as I just said a moment ago. So let's take another look, this time at a different wavelength. Now, to change the wavelength, we can choose between 1 and 17 in this case, 17 being the longest one included. So I'll enter in the number 17. Hopefully that happened. I'll press enter. I've already want to close all the earlier figures, although I could keep them. And now I'll plot this stuff all over again. And I'll go right away. Instead of dragging over the blue ones, I'll drag over the red ones, and then we'll take a look at the blue ones. So this is the prediction for N and K of the virtual substrate and of the thickness. Notice the thickness is much more accurate, and the part of the reason is the physics of the problem. Just because we're using AI doesn't mean we don't have physics underlying it. A very nice accurate solution for N, and in the first look, you first look at K and think, oh my goodness, it's missing. Well, not really. And the reason is that this scale is now times 10 to the minus 3. So the targets were between 4 and 6, because the K is low here, of a substrate, it's a silicon. So we're between 4 and 6 times 10 to the minus 3, and we're predicting a 4 times 10 to the minus 3. It's a feature of the same training system that's what we used for the others. There's another way to train for this. That's a whole other topic. And then it will become actually not necessary to train for that. So 10 to the minus 3 is pretty close to 10 to the minus 3. I'd say we've hit our target. And it shows up in those plots you saw a minute ago also. Now the other one is the first 4 numbers, and again you can see much tighter. So if you were going to make an experiment and needed to set up an ellipsometer to do real-time measurement in situ, you'd lean toward the longer wavelengths, and this would guide you to do that. Then you could use this this process. So I'll go ahead and delete all of that. No, I will not. I'll bring over the other blue lines so that I can explain what that's all about. First I have to get the right mouse. And you can see here what this is psi 1, delta 1, and for let me bring the others over so you can see them. And here's psi 3, psi 4, and here is psi 5 and delta 5. Never mind. The point being, we pull over the solutions and then push them back through the Maxwell equations to see if we get the same measured predicted value of computed psi and delta versus the psi and delta which were used in the test set. And you can see we do. I didn't include all of them. There's too many. And here they are. And this is all the long wavelength. And you can see a very nice fit there. Not so good on this first one, but not terrible because it's a bunched up range. So it takes some experience in working with these to start to understand what's happening, and I'll quickly show you an example right away. Now this is chromium on silicon with a training of a master set of 10 to the 6th. If I take the same material, chromium on silicon, with a master set of 10 to the 4th, then you're going to expect something to be probably not as accurate. It's a lot less training data. And sure enough, if I were to look at the statistics, jump right away to the statistics, I'll bring those over, and you'll see that indeed these statistics are not as good as with 10 to the 6th. So this tool here is not only allow you to explore any individual material combination that I include, you can also take a look at the effect on the statistics for various training situations, and I just included number in the set. And you can remember, I think, that we were down low here at the bottom. In fact, we could go back and take a quick look at it. That's all the longer it takes to do the calculation. Then I'll show you one more thing. So let's go back to load. We'll go chromium on silicon, but 10 to the 6th data. There it is. We'll open it up. We'll do the statistics. I'll drag them over. I'll get the other ones out of the way, and I'll drag them over. And you can look at how much tighter the statistics are if you've used 10 to the 6th. I'll just show that one. Now, you might want to know what happens when we have different thicknesses. This has all been done. I haven't mentioned it, but it's all been done at a value of 10, 13, 16, and 19 for the 4 thicknesses they're being used. Aha! What if we wanted to use a different set of thicknesses? Well, a nice way to get a good look at that is to look at the thickness calculations on the spread spectra. So I'll bring over only that, and you'll be surprised here in a moment. So there's our solutions with those thicknesses. What are they? 10. They're these numbers right here. 10, 13, 16, and 19. And sure enough, it's hitting those, and the black lines are the 10, 13, 16, 19, and the blue predictions are hitting it nicely. But what if I used a different set of thicknesses? There's 2 ways I can do that. One is I can go ahead and set this number here, and it's within a range because it's been trained within a range. The step could be 1 or it could be 4. Anything that's 1 or less, this thing just won't do anything for you, and 4 it won't because it's not been trained for that. So if I enter 3, oops, I put in 2. Let's put in 3, oops, I put in 23. Let's see what happens. If I press return, it puts back 4. It says, sorry, 4 is as high as you can go. So let's go to 3. Well, let's look at what it did. It jumped the jump of 4 for each 10. Now we're looking, instead of 10, 12, but jumps of 2, or intervals of 2, or increments, we have now increments of 4. Let's see what happens. Now that's right at the edge of the training range, so I'm not real sure what we're going to see. It's interesting to see that the values of, and I'll bring them over one by one, the prediction for the extinction coefficient of the virtual substrate are hitting the target rather nicely. And by the way, I can move this target around up and down in here, but I didn't do it in this program, but that could be done. You could also introduce error, which I've done but haven't included. You can see that these solutions at the greater thicknesses are back calculating nicely. Let's see if it got the thicknesses. Voila. Yeah, it did, especially at the longer wavelength. It's a little bit more off here. That shouldn't be surprising with a bigger thickness jump. All right. Let's try 1. I don't know how that's going to work. Let's give it a try. You can do a lot of experiments here. And it did what I wanted it to do, but it didn't do it for those two, so I'm not sure why. Let me put it in 12. It should fix this to 13. It doesn't, so I have some work to do. And it doesn't set to 1 very well. Let's try what we get as a solution. Again, N and K come out rather nicely. So that's happy. And then I won't even bring the other two over. 4. And I'll let you look at the thickness solutions, which with 1 nanometer you'd think, wow, we're stressing it. But again, at the longer wavelength, it's good. It's not too bad over here. So if you're making a system, you'd be leaning toward the longer wavelengths for that material combination. I just want to do as an experiment here. I'm going to put in 1.1 as the jump. And let's see what happens. And it does work. So I think it failed because 1 should be less than or equal, and I had less than. I didn't have less than or equal. So there we go, and that'll be very similar. You want to see it? Fair enough. We'll quickly show it. I will only bring over the thickness. Everything else looks good. And the thickness doesn't look that different from 1. These are just a 1/10 higher. Can't even really see it at this scale. So you could have the first two be small like that, and then this one, don't forget, you can't go more than 4. So let's make it be 13. And if I did everything right, it'll jump this one by 1.1 to 14.1. Let's take a look at the spectra. And I think I've shown you enough at this point in time. Let me bring that over. And you can see that I've introduced a bigger jump here. It does the predictions, and this thing can do whatever you want to come up with here. So in short, you start the program, which you've downloaded and installed from the internet. You have to load a particular set of data, which is trained networks plus other information. You want to put an increment here. It comes up 2 as a default. It can be between 1 and 4. Then we can look at the model and predictions. From spectra, we can check by doing the targets, and we can take a look at the statistics. And this button is just sitting here as a reminder of what you don't need to press that button. Well, I hope you enjoy exploring these materials, and for your attention, I salute you.